All right, guys, Mr. Antonucci here, and in this fourth video, we're going to talk about how to perform a significance test about a population when you're trying to detect a mean difference in paired data. So here's the conditions. Now, they're the same as a test for confidence intervals. So conditions for performing a significance test about a population mean or difference, or excuse me, mean difference. The paired data have to come from a random sample of a population of interest or a randomized experiment. Again, when you're sampling without replacement, the 10% condition has to be satisfied and the normal large sample condition. And I will say a note about the 10%. If you're doing an experiment, the 10% condition is not applicable there because you're not sampling, you're just doing random assignment. So the normal large sample, again, the population distribution of differences is approximately normal will satisfy that, or if the sample size is greater than or equal to 30, that will satisfy it. But if neither of those are true and you have the data, then or if you don't know the shape of the population distribution and your sample size is less than 30, then you graph the data and see if there's any strong skewness or outliers. And if there isn't, then you can proceed. Uh, Calculating the standardized test statistic in this case, you do the mean difference minus 0 over the standard error of the difference. In this case, you subtract 0 because you're the null in a significance test when you're trying to detect whether or not there's a difference is always going to be 0 for our situations here. So this is called a paired t-test for mean difference, and it's a significance test of the null hypothesis that the population mean difference is equal to a specified value. And again, typically it's going to be 0 in our situations here. So let's look at an example. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from consuming coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took the caffeine and the placebo was randomized. And this is where randomization is incorporated. It's random assignment in the experiment. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So the table displays the data of their depression scores. Higher scores correspond to more symptoms of depression. So the first line is the subjects. We just labeled them 1 through 11. The second line is their depression score with caffeine, and then the second line is without. So we want to know, do these data provide convincing evidence that caffeine withdrawal increases the depression score on average? So as always, we're going to have to do the 4-step process. So the first thing we want to do is our state step. Now here it's important that we get the difference of the depression scores with respect to whether they took the caffeine or the placebo, and indicating the direction of subtraction. So they did placebo minus caffeine. So, and these are the scores here. These are the differences, rather. And so we want the null and alternative hypothesis. So the null is that the mean difference is 0, and the alternative is that the mean difference is greater than 0. Because it's a one-tailed test, because it was asking if caffeine withdrawal increases the depression score. Okay. So we define our parameters of interest in this case, where the mean difference is placebo minus caffeine in depression test scores for caffeine-dependent people like the ones in the study. Because no significance level was specified, we're going to specify one as 0.05. And typically, if no significance level is stated in your problem, go with a 0.05 or 5%. So our plan step, state the procedure we're going to do first, paired t-test for a mean difference. Then we check the conditions. Uh, ran, Random researchers randomly assign treatments to the subjects, placebo then caffeine or caffeine then placebo. And then the normal large sample, the sample size is small, it's less than 11, and we don't know the population distribution. But if we graph a dot plot of the differences, it doesn't show any strong skewness or outliers in the graph of the data. So the normal large sample condition is satisfied. And again, the 10% condition is not necessary here because we're not sampling without replacement from a finite population. We are doing random assignment to treatment groups. So in our do step, we want to calculate the mean difference, the standard deviation of the sample mean difference, and list the sample size. Okay, we could use our calculator to do that. And then calculate the t-score, or the t-value. So that's the mean difference minus 0, which is the null hypothesized mean difference, divided by the standard error of the difference, the mean difference. And then we get 3.53. If we look at a t-distribution here, we have 10 degrees of freedom. So this is a t-distribution. If our t-score is 3.53, that's a little bit more than 3.5. That would land right here. And we're looking for the area to the right of that on the t-distribution, which would give us our p-value. According to technology, that's going to be 0.0027. And if you use a table of p-values, if you go down to 10 degrees of freedom and look for 3.53, again, it's not going to show up exactly 3.53, but 3.53 is going to be between the two t-values that correspond to a p-value of 0.0025 and 0.005. Alrighty, so we can give our conclusion at this point. Because the p-value of 0.0027 is less than our significance level, we reject the null. We have convincing evidence that caffeine withdrawal increases the depression score on average for caffeine-dependent people like the ones in this study. Okay. Now, again, since random assignment took place here, we can make inferences about subjects, cause and effect, like for subjects like the ones in this study, but we can't generalize this to the population because we didn't do random selection. Okay, so this begs the question, why did the researchers randomly assign the order in which the subjects received the placebo and caffeine in the example? And basically, the researchers wanted to be able to conclude that any statistically significant change in depression score was due to the treatments themselves and not some other variable. So randomizing the order in which they received the placebo or caffeine helps control for that possible variable. But one obvious concern is the order of treatments. Suppose the caffeine capsules were given to all the subjects in the first 2-day period. What if the weather was nicer in this 2-day period than in the second 2-day period or something like that? And they wouldn't be able to tell if the large increase in mean depression scores was due to the weather or the treatment. So random assignment of the caffeine and placebo to the 2 time periods in the experiment should help to ensure that no other variables like the weather would affect the subject's responses. So because the researchers randomly assign treatments, they can make an inference about cause and effect, like we said here. In general, there's 2 ways that an experiment with 2 treatments can yield paired data. One is that each experimental unit can be given both treatments in a random order, Or the researcher can form pairs of similar experimental units and then randomly assign each treatment to exactly one member of the pair. All right, guys, that's it for this one. Hope that was helpful to you, and take care and reach out if you have any questions.